example. Let me bring that structure. Truss structure is loading there. There you go. So this is the structure truss. With its loading, we are already given the, I would say you can think about these 4,000 and 2,000 at the bottom, like upward forces. You can think about them as reaction forces. So we are already given the values for reaction forces, and that's why, or support reactions, we already know them. And that's why we don't see any support connected to this truss. Let's just, we are starting at that point that we, let's say, draw the free body diagram and find those support reactions, and here we are. Now the problem is saying that the problem statement basically goes as determine the force in member EB. You can also add to that of the roof structure, of the roof truss, and some kind of roof simplified part of some specific building or structure truss. Also says also determine whether, I'm guessing the member, yeah, the member is in tension or compression. All right, that, let's just throw it there. We're gonna figure it out anyway. All right, so we're looking for a section where we have all the forces, right, external forces. We're looking for a section that we can make. We can't, well, the idea is to use the section method of sections. Obviously, we don't want to use the method of joints. If you want to use method of joints, we could start from C or A and then keep going till we get to E or B. But let me just say it here. Use method of joint, a method of sections, obviously. Use method of sections. So we are specifically asked to use method of sections. Why? They just wanted to make sure that you are a little touched solving this. All right. Member EB. Right? This is member EB. Right? This is the member. I'm looking for to find the force in that member. Now, possible cuts. What I can imagine is, let's say, let's use this. Let's say I make this cut. I can make that cut. If I make that cut, I'm going to have, whether you look at the left side or right side, you still are going to have 1, 2, 3, and 4 forces unknown. These internal forces become external forces. Internal forces members ED, EB, FB, and AB. They become external forces, and then they're all unknown. So 4 unknowns, that's not going to work. What is the other possibility? Make it this way. Whether you go with the right side or left side, let's go with the right side this time. You still are going to have 1, 2, 3, and 4 unknowns. So still doesn't work, right? There is no section, there is no imaginary cut that cuts through EB, which is the member I want is 4. So the cut definitely has to go through AB. There is no cut, imaginary cut, that can go through EB, and that we have enough knowns and unknown values in that that specific rigid body for one section, either left side or right side. I lost the train of my thought. Whole structure. Well, I gave you the support reactions. So what we do when we start with free body diagram of the whole structure is that, well, we start with free body diagram for the whole structure and find support reactions. But in this case, we are one step ahead of typical situation that they probably did it for us, and they provided that information. They said we have 4,000 Newton upward on B and 2,000 Newton upward on C. So there is no unknown external force that the free body diagram of the whole structure is going to help us to find. Just everything is known, as long as we are worried about, or we have to say in terms of external forces and support reactions. And any cut I look at, there is no specific cut that I can make that gives me like reasonable number of unknowns that I can use. Right? Whatever cut I make that goes through EB, it also goes through 3 other members, which we don't know their forces. So let me put it here. So later on, when you look at this, any, it should be different color. Any cut that goes through EB also goes through, or better to say cuts through, also cuts through 3 other members with, let's do it this way, members which their forces, also, yeah, this is better, which their forces are unknown. So first look, it seems like it's not going to work, right? It seems like there is no way we can solve this using method of section. However, obviously there is an however, otherwise I wouldn't have given you this problem if we couldn't solve it. Let's still make that cut. Let's still make this cut and see what we got there, what we get out of it. I'm still going to make that cut. All right, I will challenge draw. You isolate the joint, and then you would have enough known forces. Well, this works with method of joints, right? We can start from A. About A, we know everything. We can start, let's say, joint F. All right, we have, well, I don't know if it even works with method of joints. Now I'm looking at it. Well, it does. You start from A. You isolate that. Actually, you have to try this. I don't know if it works with method of joints either. Yeah, there are too many things going on there. So try and look into it using method of joint. From what I see, if you start from this joint, you have 2 known and you have 2 unknowns. But since 2 knowns are both vertical, you still might not have enough information to find A, B. Right? Since you can still find FA, and then once you know FA, you can go to joint F and use that information to find FB and FE. So if you just go one by one, you might be able to actually find, you should be able to find the force in member EB using method of joints. Yeah, starting, you might not be able to find this one, but it doesn't really matter because you can still go this way. I have to check that, but I think that works. All right, so let's draw that section. Let's draw the left side of this. Making that cut, so I have something in this, along this line. I'll try to make it as close to reality as possible. And then we have this one. All right. Let's put forces there. So this is A, this is F, this is E, and then we have our forces there. Let's use green for external forces. We have this force here, we have this force there, we have this one right there, and this one right here. And let's put the values. I'll ignore the unit, 1000, so it doesn't make it so crowded. 3,000, and this is also 1,000. Now forces that are now external forces, they used to be internal forces. I take all of them as, let's say, tension. So this one would be FAB, right? This one would be well, I guess FB, if I'm not wrong. This one would be FEB, and let's put that as FED. Hopefully I didn't miss anything. If you see something that I missed, let me know. From what I see, everything is there. All right, FEB, FFB, FAB, FED. All right. So, well, 1, 2, 3, 4 unknowns, right? Not a good situation, but there is a way around this. If I look at this cut, I cannot find FEB there, but I might be able to find a different force. Right, looking at this, let's follow the line of actions for these forces. This is here, and this is there. They all meet at point B, or they should, if I draw it in a bad way. So, something interesting. If I find the moment about point B, I can eliminate everything, and the only thing left would be FED. So I might not be able to find all the forces right here, but I can find FED by looking at this. Let's write this equation. Summation of moments about point B is equal to 0. And let's take this as positive. So from what I see, FEB does not make any moment about point B. FB does not make any. FAB does not make any moment. So all three are gone. 1,000 Newton force downward is not also making any moment about point B. That the one applied to joint E. So only things left are 3 known forces: 3,000 downward, 1,000 downward applied at joint A, 4,000 upward applied at joint A, and FED. So theoretically, or mathematically speaking, I can find FED. Now, is it the force in EB? No, but that's what's going to help me, right? I can use that and find FEB later on. I pretty much at this point, we're kind of desperate, so we get whatever we can from this free body diagram, and we can get FED. Let's see where does that take us. So I'm finding moment about point B. At this point, you should be very comfortable with this. 4,000. Pretty bad handwriting. 4,000 multiplied by 4. Right, that upward force, and then the direction is this way, so it should be negative. 1,000 is there, so 1,000 multiplied by 4 also, and direction is positive. I have 3,000 there. The distance, the perpendicular distance from that 3,000 Newton force and joint B is 2 meters. It's going to create a positive moment, so that would be plus 3,000 times the distance, which is 2. Right? Let me move this a little bit so if you type something, I can see. All right. And the last one is FED. Now, how do we find the FED? The moments created by FED about point B. Remember, goes back to the whole idea of principle of moments. Remember, we said the moment created about a point by a given force is equal to the vector sum of all the moments created by the components of that force about that point. Exactly. Thank you. So that's what I'm going to do. As Elizabeth said, right? If we decompose this one, let me use a color that is more visible there, or at least I think it would be more visible. That would be FEDX. This would be FEDY. Not sure if that was the best choice of color, but all right. So to get those components, I need to know this angle. That's the worst choice of color. There you go. I need to know this angle. Let's just call this theta. Yeah, I went with pink. Theta is equal to, what is the value for theta? Go back to the general structure there, the whole structure. This is a horizontal line. This is a horizontal line. This is a line that is cutting these two horizontal lines. Exactly, Richard. It's 30 degrees. If this is 30 degrees, this also is 30 degrees. This is also theta. So theta is 30 degrees. So that'll give me, well, FEDY is passing through B. Its line of action is passing through point B, so no component there. I'm going to get FED. FEDX would be FED cosine, I believe, if I'm not wrong. Cosine 30 degrees. Did I get the, I put the wrong angle there. This angle is equal to this one. So this one is 30 degrees. This is 60 degrees. All right. This becomes 60 degrees. This theta is 30 degrees. All right, you're right. This is not theta though. Let's just call it something else. This angle is 30 degrees. All right. But the angle I mentioned is this one, which actually it's still going to be 30 degrees. Yeah, it's still going to be 30 degrees. You're right. So 30 degrees doesn't matter. All right, because this is also 30 degrees and that is equal to the same thing. So FEDX, well, whatever is FED, I'm making a mistake here. Let me double check. Let's draw it here. FED, this is FEDX, this is FEDY. I got this at 30 degrees. I'm looking for, yeah, cosine 30 degrees, I guess. I don't see the problem. And that would be negative. Minus is equal to 0. All right. Can someone do this math? I actually don't have the answer to that. So that's, and seems like I don't even have, oh, there you go, my calculator here. So if you're sitting there, use this time to do this math, and hopefully we all get the same answer. Times 4 plus 1000 times 4. And if you see a mistake somewhere, let me know. 3000 times 2 divided by cosine 30 degrees. I got 4000 minus 4000 times 4 plus 1000 times 4 plus 3000 times 2, 6000 divided by cosine 30 degrees. Something about this problem is bugging me. All right. FED turned out to be minus 6,928 point, actually not minus, plus, yeah, 0.2 newtons. All right. We got this right. And this is FED. Right now, what did I want FED for? That's the question. That why they look for FED. Now the question is, how does that help me? Right, so I found FED. Now the problem was I wanted to find the force in EB. From this free body diagram, I cannot get that much. right? Because if I start writing the equations in along x and y directions, there is not that much there that can help me. And the reason is, well, we can probably see the reason. If I write it in the y direction, would be fe dy, then fb also has a component in y direction, so there are two unknowns there. If I write it in x direction, fedx is one component that I know, but I don't know fab, and fb also is going to have a component in x direction. So I'm going to have two unknowns. I'm going to have three unknowns eventually, I believe, that two equations are not going to help me to find them. So what should I do next? Now, this is the, I would say probably an unusual cut we're going to make. I would say very similar to the way we were doing method of joints, right? What I will do is that I'll come, and you might ask me, how did I come up with that? I'll give you the answer that a professor long time ago gave me when I asked a question regarding one of these problems that he basically, as we call these, uh, you took something out of your hat suddenly and say, well, that's the way. I'll give you the same answer he gave me. Experience, my friend, experience. That's how I figured it out. FED, well, I think I put it correctly. 4 times 4 plus 1000 times 4 plus 3000 times 2. That's negative. You're right. That becomes negative. So it should be negative. In my mind, I moved it to the other side. Who said positive? I'm looking at you, Samo. All right. That should be negative. Yeah. Because that goes to the other side. This side is negative, so it becomes negative. All right. So, well, the direction should be switched, obviously, in free body diagram, if you want to have a correct free body diagram. So, what is next? Now, what I'm going to do, I'm going to make a another unusual cut. I'll make a cut. Let me clean this up. This is very crowded here. It's hard to see. I'll make, it's still crowded. All right, this is as fast as this tool goes. All right. And that was the cut that we make AA. Right, keep it. I'm going to make another cut. I'm going to make this cut. Very weird cut. Maybe I can do it. As we said, if one part of the structure, if the whole structure is under equilibrium, every part of it should be under equilibrium. Now you might say, well, what is the difference between this cut and a joint method? I would say that's pretty much joint method. I'm kind of cheating here. You could just look at that joint and say, well, I'm going to use joint method here and look at the forces on joint E and find the force I want. That would be correct. This cut is nothing but just joint method. I'm isolating the part of the structure that only includes that joint. Is it correct? Yeah, it's still a cut. So cut, let me write here. This is cut AA, and this is cut BB. Since I was told in the problem I can use only method of section, I kind of cheated. Right? I said, well, this is my section. So section BB, if you look at it, very interesting section. This is E. And then we have this one, and this one. FED, we have to switch the direction. Let me just put in the right direction here then. There you go. FED. This one is downward. Let me put the external force. This is 1000. And I actually don't know about this, but we can just put it in either direction. Let's put it in this direction and put this one in this direction. I'm actually not sure. I'm just guessing these directions. So this becomes FEB, and this one is FEF. So, yeah, I know. This is pretty much method of joint. As I said, I'm cheating. Fx is equal to 0, summation of forces. We already know this angle is 30 degrees. Right there, 30 degrees. So I call this theta. So what I get? I'll get FEF cosine 30 degrees minus FED cosine 30 degrees is equal to 0. I was looking for. So this one directly gives me FEF. FEF is equal to FED, which is, now it's not negative because I flipped the direction. So that's 6928.2 newtons. This is FEF. Still not what I wanted though. I'm looking for EB. But there you go. We can write this in Y direction and take this as positive. This becomes minus 1000 minus FEB plus FEF sine theta plus FED sine theta is equal to 0. Hopefully I didn't make any mistake. 1000 minus FEB, FEF sine theta, FED sine theta. Keep in mind this is symmetric, so this is also theta. All right. From there, you should be able to get FEB. So you know already, let me put the knowns there. Well, this 1000 FEF, we know it's 6928.2. Theta we know is 30 degrees. Theta we know is 30 degrees. And FEF we know is also equal to 6928.2. So since pretty much everything is equal, if I you do have to do the math there. I'll leave it to you guys. Newtons, right? Really cheating during solving this problem. All right. So that was a little different. Right? You can look at it as a combination of method of sections and joint. You can look at it as two sections. Section A is a typical section we make. Section BB is very unusual. It's pretty much similar to the method of joint. I just isolated that joint and did it.